CPS Synergy Resilient Wireless Sensor Actuator Networks. Wireless sensor actuator networks consist of numerous sensing and actuation devices that coordinate their activities over a wireless comm network. This project addresses the issue of resilience in YSENS. A resilient system is one that maintains an active awareness of surrounding threats and reacts to those threats in a manner that returns the system to operational normalcy in finite time. The objective of this project is to develop YSENS that are resilient to faults in the underlying comm network. This will be done through the coordinated management of the YSENS control and communication functions. The methods will be evaluated on a multi-robot testbed consisting of both ground and aerial vehicles, using machine-to-machine or M2M communication technologies. The project's objectives are to develop methods that optimally control the channel's physical layer in a manner that enforces probabilistic bounds on channel burstiness. Develop methods that optimally switch the control application structure in response to abrupt fades in the channel state. Develop an autonomous multi-robot testbed consisting of ground and aerial vehicles for evaluation of resilient control and task coordination algorithms, and the development of M2M hardware and middleware to support the control algorithm and project testbed. The project's approach rests on two fundamental trends. One trend concerns machine-to-machine communication networks that promise greater peak bit rates and reliability. Another trend concerns the use of dynamic quantization and event-triggered feedback to reduce the bit rates required for safety and stability. What is M2M communication? Machine-to-machine or M2M technologies build upon significant advances and economies of scale of the commercial wireless industry surrounding the 3GPP long-term evolution, mobile cellular, and IEEE 802.11 wireless LAN family of standards. Chipsets for both standards can achieve maximum data rates of 10 to 100 megabits per second through the coordinated use of orthogonal frequency division multiplexing and adaptive modulation encoding schemes. This CPS project will develop middleware providing the control application with neighbor discovery, quality of service control, multiple access, and routing on top of these advanced physical layers. The development environment we're proposing to use involves a gumsticks platform incorporating the latest IEEE 802.11 interfaces. Wireless communication channels are inherently bursty. This burstiness can result in channel outages of relatively long duration. Formal modeling of such fading channels is often done using a two-state Markov chain. Another useful model for bursty channels characterizes the likelihood of long outages. If we let R denote the number of received bits, then the channel has exponentially bounded burstiness, or as EBB, if there exists a constant beta such that the probability of receiving more than sigma bits in a single transmission is less than e to the minus beta sigma for all sigma greater than 0. In other words, a channel is EBB if the likelihood of long outages scales in an exponential manner with burst length. EBB channel models are used because it is a more realistic model of wireless channel outages. It can be related back to existing two-state Markov chain models. But more importantly, it has a close connection to strong probabilistic stability concepts such as almost shear stability. And we feel that these stability concepts provide a good framework in which to develop safety-critical systems. Traditional mean-square stability is often used to study the behavior or performance of network control systems. But MSS is inadequate for most safety-critical systems because of the bursty channels they might have. This is because an MSS system will still exhibit large deviations away from its equilibrium point. Almost shear stability provides a stronger stability concept that is well suited to safety-critical systems. Almost shear stability bounds the likelihood of a system state deviating from its equilibrium point by an exponential function of time, so that the probability that the state x of k at time k is further than epsilon from its equilibrium point is less than an exponential function of time. This stability concept has much in common with the EBB channel model, and it suggests that if one can control the network so its bursts are EBB, then one can guarantee a stronger safety-critical stability concept, such as almost shear stability. This project has established conditions under which a network system that has almost shear practical stability when the communication channel is EBB. We are currently applying these concepts to multi-robot formation control. The stochastic control concepts we discussed earlier are being implemented on a multi-vehicle leader-follower application. Formation consists of a platoon of ground vehicles coordinating their actions over a communication tree, in which each node's leaf is a follower. The system is viewed as a string of leader-follower pairs. In the current testbed, we use XB radios for inter-vehicle communication. In future work, we'll use M2M radio modules. Our formation control uses a novel switching scheme that switches to less aggressive controllers when the channel state is poor. This decision is conditioned on prior information about the relation between channel state and the physical state of the vehicles. The switching strategy makes use of an EBB channel model and hence is able to assure almost shear practical stability even in the presence of deep channel fades. The following simulation results confirm the almost shear nature of the leader-follower system, in that the worst case and best case system trajectories all asymptotically converge to the equilibrium point. We are currently working to implement this control strategy in the multi-robotic testbed at the University of Notre Dame. Resilient controls and wireless networking technologies will be evaluated on an indoor and outdoor multi-robot testbed consisting of ground and aerial vehicles communicating over an M2M wireless comm network. The Discover facility at the University of Notre Dame was founded with the support of this project. The testbed consists of several ground and aerial vehicles whose indoor position is tracked using a 24-camera off-the-track motion capture system. The main outcomes of this project today are itemized below. We have developed a framework for coordinated control of multiple vehicles communicating over wireless channels exhibiting deep fades. We have constructed and are continuing the development of a new multi-robot testbed facility, the Discover Lab, at the University of Notre Dame. The novelty in this testbed rests in its focus on multi-robot swarm resilience and its use of M2M communication technologies. And finally, we've begun development of a commercially oriented M2M module based on gum stick devices with embedded IEEE 802.11g. Devices have been successfully tested with the Discover Labs ground robot testbed. In future work, we'll develop middleware for these modules that work well with the control tasks in the testbed.